that. When we left off, we were here. We were looking at what is just another representation of graphical models. In fact, these are graphical models that we've seen before. This first one is like a mixture of Gaussians, which you know intimately after the last homework assignment. So we had said that we have directed graphs where for every random variable we will have this node, right, is the node that represents this random variable, and it might be dependent on things. It might be dependent on its parents, in this case the h and this other thing. Yeah. So if we have a node like this and a node like this, everything is clear. We might also say, well, I might have a lot of pixels with a lot of h's. So do I have to draw every one of them again and again? If I have a million pixels in my image, I have a megapixel image, do I have to draw my problem that way? No, in fact, you could say you have I such elements, I such pairs, and this is a plate. So we're just saying that there are I plates. Inside of every plate there is this dependency of x is dependent on h. So with this plate, we know how many of them there are. You can imagine that if you needed to write it out longhand, you would just replicate that over and over again. The other thing we have are bullets. I said x is dependent on h, and it's also dependent on this other thing. Let's start with maybe h. H is dependent on lambda. What do you think is the difference? Why do we have a bullet here instead of a node?
Because it's a parameter, not a random variable.
Because it's a fixed parameter and not a random variable. That's right. So we are saying we need to know what lambda is. That will change what h does, but it's not something we're worried about having a distribution over. We're just going to have a value of lambda, and that's it. Similarly here, we're just going to have a value of, in this case, a mu and a sigma. So we could say, well, we have maybe two bullets, but this is now getting even more shorthand. We're saying, okay, here are these parameters, mu and sigma. How many of them do we have? Right? K of them. So we can have a plate on that as well. And so you should be recognizing our mixture of Gaussians here. We're saying, yeah, we might have I data points. For each of the I data points, we also have a hidden parameter. So that's why we have I of these. For this x, we're going to try to explain it using one of a mixture of Gaussians. How many Gaussians do we have? K of them. Each Gaussian is controlled using these parameters. All right, so that's the mixture of Gaussians summarized visually. This is the t-distribution summarized visually. There's also a hidden parameter, except now there's no lambda on it, and we only have one, so to speak, Gaussian, right? It's a t-distribution, so we have mu, sigma, and nu. We don't have k of them because the t-distribution, we said by definition, is as if you took an infinite number of Gaussians all at the same mean with every possible variance, but preferring small variances. Okay. And then finally, factor analyzer. We didn't talk about it much, but this is the graphical representation for it. Okay, so we're going to press on from here, but the idea is you now know when someone talks about graphical models, when we say I'd like you to plot for me a graphical model with these random variables, these parameters, and my problem is yay big, you should be able to do this kind of graphic. All right. Now, we've been talking about directed graphs with arrows. We said those are Bayesian networks. We can also have what are called Markov networks with undirected edges. So these will just be nodes with a line between them, no arrow pointing in either direction. Now, remember, we're still dealing with the same problem that we might have multiple world states or multiple pixels or things about the world that we want to measure, and we want to compute the joint probability over all of those random variables at the same time. We don't want to assume that they're all completely independent. We don't want to assume they're all completely dependent, right? Because that gets us into trouble with too many parameters. We want to model which ones are dependent on which. With the directed graph, where we had arrows, we were always looking at the parents of a node. We said, you are clearly dependent on your parents. And in fact, you're also dependent on everyone in your Markov blanket, if you remember that. Okay. So in the undirected graph, we're going to have very similar functionality. We're going to say, all right, the joint probability over all of my random variables is going to be based on looking at little sets of my graphical model, little collections of variables, not all of them, but subsets of all of them, and multiplying together this potential function that we're going to see at for each set. So we'll see more examples of potential functions, but for now, keep in mind that potential is good. We want, if we think that we have our variables in a very high probability state, like this is a likely situation, that means that we had lots of high potential states. Potential between different nodes in our graphical models was very high. In fact, it's non-negative, but it could be zero in the worst case. That would be a very low potential. All right. Now the slightly, and so maybe this is slightly confusing. So let's sort of put a gap here and say we were using phi's in the previous weeks before reading week. We were using phi's to mean our parameter weights, right? Our gradients when doing classification or regression, right? And now we're going to recycle. We're going to use phi for something else. Now we're using it for this potential function. And in fact, we're going to recycle both phi and psi. So let me just right here, right? Potential. That's enough. All right. C is the number of sets or cliques that we're going to worry about. I'll introduce the word cliques in just a moment. But then let me explain Z here. On the left, we're talking about probability. With directed graphs, we were talking about probabilities, right? We were talking about how to factorize them. Let's say that's the normal way, the easy way of doing it. If I introduce some kind of potential function called phi, it measures potential. It returns non-negative values. That doesn't mean that I've got probabilities, right? To really talk about probability of some combination of my variables, I have to normalize. I have to normalize by what are all the other possible things that could have happened with my random variables. That could potentially be a lot of other things. We were talking about pixels being apple or not apple, and if we have 2 pixels or 3 or 4, right, this problem gets more and more complicated because it's possible that any 1 or 2 or 3 of those variables is different than the others. So if I say, what's the probability of all of my 10 pixels being apple, you have to take into account that there are 10 pixels, right? And that each one of them could be apple or not apple. So this is our normalizing term, 1 over z in the front, where z is trying to add up all of these possible scenarios, right? What would happen if you had, and so here, this is where I was writing out sort of for 4 pixels, I was saying you could have, those are supposed to be pixels, sorry, and then this would be 0, 0, w equals 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, etc., right? Now, for very large systems, this might be a very big summation. So actually computing any kind of non-trivial phi. I haven't told you a phi yet, right? So you're okay with that? We'll get to phi's in just a moment. If I give you some phi that's non-trivial, you're going to have to sit here and perform this calculation over many, many variables. That's not great. We may have to learn to live with it. In general, we'll be able to say, oh, one of these, if I take this without the normalizing constant, we can say, well, one of these is greater than the other, so one of them is more likely than the other. But of course, until we have a normalizing term, we may not be able to actually express a probability, right? Where you would normally threshold the probability at 0.5 or something like that. All right, so keep in mind, that's the normalizing constant. We'll mention it again in a moment. All right, so there's an alternative formulation to this. This is what we've been talking about with phi's. And I warned you there was going to be a potential change. Now, you should be anticipating this because there was this product here. As soon as there's a product, again and again, you've seen throughout this class, you tend to say, oh, that's really difficult to work with. Maybe if we take the log of that, then we can talk about sums instead. And sure enough, we're going to do the same thing here. In fact, we take the negative log, and so this psi sub c, I don't know if you can read that here, psi sub c equals negative log of phi sub c, of the same combination of variables. So we might have x1 through xn. Here we have x1 through xn again. Psi equals the negative log of phi. So let me write this down. And this we're calling the cost function. I'm just writing them down because they're going to go away in a moment. I want you to be able to refer back to them. Are you able to see anything on the whiteboard? Yes? Okay. We wanted these to be high or low for something that's probable. High. Okay. Because now we've taken the negative log of that term, so now we've ended up with a summation instead. Do we want the cost function to be high or low for something that's probable? Louder?
Low.
Low. Okay. Good. So cost is bad. We want low cost things. If we have a high cost, that means it's an improbable combination of states. All right? Yes, by the way, this is referred to as a Gibbs distribution, and we probably won't have time to talk about chapter 10's explanation of Gibbs sampling, but it's a very short summary in the book, and it's not that complicated. It's quite straightforward. You're basically halfway there. All right. So I said for these potential functions, we're going to multiply by over the potential functions, and inside of each potential function, we're going to look at not one of the variables, not all of the variables, but some subset of our different variables. So this subset, indexed with a C, as you see here, is referring to, I don't like this word very much, but it's a clique or a collection, if you prefer. So you can think of C as clique or C as collection. And you'll see in a moment what that means, but it says this is a collection of random variables, and the same random variable may be present in different cliques. So we had a similar slide for directed graphs. Now we have one for undirected graphs. If you are trying to visualize some equation, you're going to draw it by drawing a random variable as a node, and by connecting edges between random variables that are dependent on each other. And you're not going to draw edges between random variables that are independent of each other. Now, dependence and conditional independence will become apparent in a moment. Just briefly, to go the other way, you're going to look at a picture, and when you want to factorize it, you're going to try to identify one of these potential terms for every maximal clique. A maximal clique is a very special kind of clique. So let me explain all of that with a visual example. Right. So this is going to be easier, I hope, than figuring out the Markov blanket for our directed graph. But there's a reason to do both. We'll come back to that. So we have our graphical representation. There are 3 nodes. There are no arrows. These are 3 nodes related to each other via x2. Our probability, our joint probability on x1, x2, x3 is this normalizing constant, 1 over z. We know we could compute it for 3 variables. It wouldn't be so bad. 1 over z times phi1, it's this potential function, over x1 and x2, because it's looking at this edge and it's saying, yeah, I'm going to call this a clique. So this is a set, a collection. So I'm going to evaluate what is the probability, what does the potential function say about this collection? How probable is it? And then there's a phi2 that does the same thing for these other 2 nodes. Straightforward? Yeah? Right. So I'll press on. X1 is conditionally independent of x3 given x2. In this case, we don't have to worry about which way the arrows are pointing. We don't have to worry about whose parent is whose, right? Or who is a parent of one of my children, right? You just say, okay, who's connected with an edge? If you're not connected with an edge, we're conditionally independent of each other. To determine the state of x1, all I need to know is x2. Getting a hint about x3 won't help at all. So you could say that the route is blocked by x2. We have a similar proof to what we did last time. I won't belabor it, but in the same way as before, the potential, when I'm trying to compute the conditional probability of x1, given all of this information, it turns out that the potential function x2, x3 is a constant when it comes to marginalizing out x1. So if you were here on Tuesday, you saw that moves out front. It's just a product. It's in the numerator and the denominator cancels out, and we have a final expression for this conditional probability that doesn't have an x3 in it. Doesn't depend on x3, doesn't care what x3 is doing, just cares on what x2 is doing. Now, that was a simple graph. Now this is a more complicated graph. And this is where we're going to finally see what it means to be a clique versus a maximal clique. We can make a clique out of any 2 nodes that are connected by an edge. We can, so let's see. Here there's a clique 4, 5, sort of burgundy one. It says, all right, this is clique 4, 5. It includes 2 variables in it. I might have phi number 4, 5, and it's going to have a set of 2 variables in its set of nodes. We also have cliques for this pair. While we could have a clique for x1, x3, we prefer, if we can, not to do that. Because if we can, we'd like to decompose this picture, or any other one that I show you in the future. You prefer to decompose it into maximal cliques. And a maximal clique is one where you cannot add another node which would be independent of the things you already have in your set. So we have here clique 1, 2, 3, which is a maximal clique. Everything inside a maximal clique is connected to everything else in the maximal clique. 1 is connected to 2, 1 is connected to 3, and all 3 are connected to each other. It's a fully connected graph when we just look at those 3. If it weren't a maximally connected, if it weren't a maximal clique, then we would be able to say add variable x4 to it. We'd be able to say, ah, great, x4 is part of our group. But we can't add x4 because even though it's connected to one of our members, x4 isn't connected to x1 and x4 isn't connected to x3, not directly. So x1, 2, 3 is a maximal clique. And are there any other maximal cliques bigger than the pairs that I've already pointed out? Some are shaking heads. No, that's right. There's nothing else you can do. You try to add something to this pair, and it's not going to work, right? No, everything else is not fully connected. So a maximal clique inside of itself is fully connected, and it can't be expanded by adding any other node. All right. When we factorize this, this will become a little bit clearer why it's attractive to do this. Remember, we're just doing joint probability of all 5 of our variables. We're saying, okay, great, there's this normalizing term 1 over z. Let's not worry about z right now. We could write it out if we wanted to. We're going to have a phi term, and inside of this phi, it's phi for clique number 1. Clique number 1 is going to have these 3 variables, 1, 2, 3. Clique number 2 is going to have these 2, 2 and 4. 3 has 3 and 5. 4 has 4 and 5. Because we decompose this graph into its set of maximal cliques, which is 4 of them, then we know that there have to be 4 terms. Yes, technically and practically, you are allowed to say, I'm going to have more than 4 terms, and I'm just going to have little cliques, not maximal ones, and I'll just make 1, 2 its own clique, I'll make 1, 3 its own clique, this its own clique, this its own clique, this is, and in the end, you would get the same probability, you just have more terms. So there's only one unique decomposition of this graph into its maximal cliques, which gives you the smallest number of terms, right? The smallest number of potential functions that you have to worry about. And there's obviously a non-unique, or there's a space of possible decompositions of this into just pairwise cliques, or smaller sets than what we're seeing here. Normally, we prefer the one that's unique, because then we can talk about, okay, finding the maximal and reduce the number of potential functions. All right. So, I think I've already pointed this out, right? That is equivalent to breaking it up into just the pairs. Now, we've got directed and undirected graphs. You're thinking, why did you tell us about one and the other? Don't they just do the same thing? So, some conditional independent situations can be explained equally by both types of graph. Some can only be represented by directed and others by undirected. And in fact, there are some situations that can't be represented by either. And so that we'll sort of get to that later. But to give you some examples. Here are 2 graphs that represent the exact same thing. In both of them, x2 is conditionally independent of x1 given x3. Can we see that? x1 is conditionally independent of x2 as long as we're given x3. And what you're seeing here in the pink is the Markov blanket for x2. Right, remember conditional independence, we can flip this part around, always given x3. In this case, because it's undirected, nothing changes. It's actually the same. x2 is conditionally independent of x1, right? Because it's the path from x1 to x2 is blocked by x3. So given x3, we have the same situation as we had in the directed graph. Now, if we have these 3 nodes arranged inside of a directed graph, there's no undirected version of this graph. There's no undirected version that will say, yes, x2 is independent of x1. Right? Because if we replace this somehow, then we'll just have this again. That will make us dependent on x3. Here, x2 and x1 are independent. This is where I was going on holiday and you were going on holiday and taking very different pictures. And we were saying, yep, we're taking pictures independently of each other. Makes no difference. One doesn't affect the other. Yes?
So in the second diagram, is that the shaded section the maximal clique of x2?
It is. Yeah. The shaded area is representing the Markov blanket, i.e. the variables that are sufficient to wholly explain the probability of what's happening at x2. Anything outside of the Markov blanket doesn't help us at all with the red variable. Mm-hmm. Now, it just so happens that we normally don't even bother talking about the Markov blanket for undirected graphs because it's just who is connected to me directly. But yes, that's a good interpretation. All right, so another set of examples. Undirected, right? X1 and X4 are not connected to each other directly. This is an undirected graph, clearly. So X1 is independent of X4 as long as we're given X2 and X3. So X1 independent of X4 given X2 and X3. We don't just have to look at it top bottom, we can look at it left right. X2 is independent of X3 given the other two. All right, now you try to arrange a directed graph in a similar shape, and you're not going to get the same results. Remember, this was X1 independent of X4 given X2 and X3. Yes, X1 is independent of X4 given X2 and X3. Here, X1 is the parent. X4 is sort of the offspring in two different ways. So we have to be given X2 and X3. But while here, X2 is independent of X3 given X1 and X4, right? We said that's independent of that given the north and south nodes. Here, X2 is independent of X3 only given X1. X4 is unnecessary here because of the direction of the arrows. So if you want to express some kind of conditional independence, it may be that you could represent it using directed graphs or undirected graphs, or it might be that you're stuck, that you have to represent it using just one or just the other. It's a bit of a puzzle to figure out which one is appropriate for your problem. So let me just introduce this one example. This is in fact the example that we'll be using for your chapter 11. So we're going to spring off in basically just a moment. Some of you might have heard of hidden Markov models. This is them. This is what we've been working toward. We're mostly going to look at things from the directed graph kind of way, but there are parallels to be drawn. So we've been talking about our random variables. We've been saying that we'll have arrows connecting the ones that are dependent on each other. Here we're saying we're going to have a whole bunch of world states, which the world states correspond to some phrase or sentence that we're expressing using sign language. So maybe I'm saying that I want banana. I don't know what the symbol is for banana. And the world states are all the different things that I could express using sign language, all the different symbols. Now, the chances of me saying banana as the first word may be very small, right? So that would be kind of the prior on what's happening here. The chances of me sort of speaking like Yoda and transposing all the different words in a random jumble are pretty low. So, in fact, it might be that there is a very specific order to things. That if I say I want, then there's going to be some very high probability of fruits here, and not some other words. So we're going to have this representation of a chain to capture the fact that our expression of world states that we're interested in is also a chain. That's the world states, right? That's the state the world is in. Our observations, just like all along, whether it was RGB or silhouettes or something like that are going to be captured in the x's. And what we're saying here is that our x's are only connected to those individual word states. In other words, this x, I mean, it's just a snapshot. The snapshot itself isn't related to the other photographs, right? The thing that's important about it is that it relates to that particular world state. So in this, and now we're going to jump over from this example in chapter 10. Let me get out of here to that example in chapter 11. So if you're following along in the notes, let's go to chains. All right, we've already motivated all of this. Large number of variables n. We're going to start with the chain model. I'll hint that we're going to talk about, eventually we're going to talk about trees and grids. For now, I'm just talking about the layout of the nodes, right? The nodes are the variables that we've been seeing. But today we're just worried about chains, that's both now and in the practical. We're going to assume that we have discrete world states Wn, so whether they are vocabulary words in my sign language vocabulary, or something else that's discrete. You'll be doing stereo actually in the lab. We have observed data x for each world state, and we say that the data x is conditionally independent of all other data that we might observe, given the world state that it's attached to. It's only representing the world state that it's attached to. So this is a real world example. This is a friend of mine, Thad Starner. He's one of the original so-called Borg people introducing sort of wearable computing, and that's it's a retina display. So he built what I think is the first sign language recognition system. It would be a camera mounted inside of a baseball cap pointing down at his hands so you can see this. He'd previously done versions where it was sort of a camera, hooked up to a big supercomputer, and it was trying to do this particular task. So I've already introduced it, right? You're going to see a bunch of observations, x1, x2, x3, and x1 is attached to w1, x2 is attached to w2, and so on, for some length of phrase. Fixed length phrase for now, okay? I'm just going to say there are n words that I'm going to speak in my sign language expression. All right. And the interesting thing here is for each of these relationships, we're talking about the probability of x1 given w1. So our total probability, our joint probability over all of the data and world variables, these are all random variables, right? Our joint probability over all of them is going to be this product where we look at the individual pairs, probability of xn given wn, probability of x1 given w1, times probability of x2 given w2, etc., over n observations, so n frames in our video, multiplied by the world potentials here, right? Or sorry, we haven't moved to potentials. Or world probabilities. Probability of wn given wn minus 1. So probability of wn given wn minus 1. So can you spot what's missing here? There's a hint.
Distribution.
Sorry?
The star thing, distribution.
The star distribution. Yeah? Does anyone else see this? If we start at n equals 2, so that'll be 2, that'll be wn minus 1, that's probability of w1. Technically, we should also have in here, or maybe right in front of this, probability of w1. Okay. Prior on what is the first state. So we're going to brush that under the rug. We're just going to say, okay, just assume it's a uniform prior. I'm equally likely to start any one of the possible things I might say at first. Of course, that's not entirely fair because even if it's a uniform distribution, it's going to lower the probability, right? Because it's going to be something between 0 and 1. multiplied by this full product. So our joint probability will just be lowered. But it's going to be lowered by the same amount if I have a uniform distribution. So we kind of proceed from there. The other thing is that this, if we kind of neglect that for now, it allows us to say, look, they're equivalent. That directed graph is equivalent to this undirected graph, right? Which is a rare coincidence where everything comes together, although we might have had to cheat a little bit. All right, I'm not going to belabor this, you've just seen it, right? We can turn our probabilities, right? These are the probabilities between the W's. These are the probabilities between each W and its observation X into potential functions, right? So we have this potential function, again, between the data and this world state, potential functions, zeta, between our world states. All right, and we still have we now have our Z normalization term out in front. So we can say that they are equivalent, right? This is the directed, this is the undirected one, right? Arrows, no arrows. If we say, yeah, you know what? If I take this big Z and define it to be this product of little z and little z prime, I can separate them. So there's a little z here for the data-based term and a z prime for the world state-based term, the term that always looks back to the previous state. And in this way, we have two models representing basically the same thing. All right. So it's an important slide because it represents all the things we're going to skip for now. Normally what we would do is we would say, here's this model. We're setting up a model. Here's how you plug in your data. Okay, now we're going to train it, right? And we're going to skip the training part for now. But the model we still have to talk about. So we're going to say, right, so I need to have two things, right? Probability of probability of X given W, and probability of W given the previous W in the Markov model in the chain. We're looking at these types of images, right? So we're going to make, I mean, I could ask you, but you would probably guess this yourselves. We're going to say, all right, fine, the probability of a given X is just going to be a Gaussian. We'll just assume that given that you are expressing the phrase for want, right? If Wn equals the want situation, you're basically going to look the same. Your pixels will be roughly the same, subject to some plus or minus some noise. Okay. Maybe it's not a great assumption. Maybe, in fact, your hand will vary quite wildly. But let's just for now assume that we can capture all the different versions of want with a Gaussian. So we have a normal distribution on what X might be doing, what the nth X might be doing. Right? So we have this X will be different than this X, right? Normal distribution for this term that's talking about the data. The term that's talking about the state, given the previous state, well, this has to be a categorical distribution, doesn't it? We've got a bunch of discrete states of the world. So we are just going to say, yeah, you're in one of these k discrete states. And of course, it all depends on what was your previous state. Normally, we would say, okay, we have three sets of parameters here. We have three parameters: our mean, covariance, and our lambdas. We should take some training data, optimize with respect to our parameters so that we get the best possible parameters, and only then do we move on to inference. Today, we're going to make some assumptions. I'm going to give you some parameters. I'm going to say, these are great parameters, trust me, you'll love these parameters and use them. And in fact, you'll do that in your lab today. Training the parameters isn't always easy. There's a very brief summary of it in section 11.6. We might get to it tomorrow. We're definitely not getting to it today. So, trust me for now, parameters can be found. And then, when you're done training, you can use them to do inference. So now we're going to do maximum a posteriori inference in chain models. This is going to lead us to the Viterbi algorithm. If you've heard of it, whether you have or not, please pay attention because you're going to have to implement this. We said we've got a directed model. Nothing has changed. We're not worried about our W sub 1, probability W sub 1. So we're just going to press on. If we want to do maximum posteriori inference, we want to find, I mean, this is the point of what we're doing, right? We're trying to find what did that person say? What did that woman gesture in her video? We want to know what she said in the first frame, in the second, and the nth frame. I mean, the quick version of that is, well, let's pick the combination of world states that maximizes the joint probability. Okay, now it so happens that yes, the joint probability, right? We could write this out as probability of. Let me do that actually. So our getting a little low. Let me just say our probability of x's and our w's jointly. Probability of x given w times probability of w, and Bayes' rule tells us that equals. Help me out.
Probability of x and w.
Probability, we already have probability of x given w times probability of w. W given x times probability of x. Okay. So if we have this, we know that we can move the term probability of x over to the other side. This is like our normalizing term. And so we're left with probability of w given x. Right. But the point isn't to go back, the point is to go forward. We have this probability, we're trying to maximize this thing. Maximizing this thing is equivalent to minimizing the negative log of that thing. Right? Everybody's okay with that? Maximize that is the same as minimizing the negative log of that. That thing, by the way, well, we have an equation for it. That's there. It's these two terms that we're going to take the product of. The great thing is we're taking a log of a product. So log of a times b, right, means that now we're adding the log of a and the log of b. So it happens that we've got a negative log. Okay, so we were minimizing, we're still minimizing, except now instead of two multiplied terms, we've got these two summations. And the log moves inside, so the log of this probability and the log of this particular probability. So you should see if this is our directed model, and we agree that that is, right? That's quite comfortable. And we know we're trying to maximize this joint probability. It breaks down to two elements, two sums like this. And we want to find the world state. The answer to all of our questions is the combination of w's that we come up with that would minimize this overall term. Now we're going to take this equation, slide it up. We don't have much further to go. Slide that up, and we say, you know what, this is quite unwieldy, a little bit difficult to write it all out. Let's make ourselves a shorthand version, and this is what I'm going to refer to when we go through our little demo now. We're going to go through a demo where I'm going to refer to this as the unary term. That whole thing, the sum here is still the sum, but it's over the unary term of Wn. Unary of Wn means I'm looking at Wn and I'm asking how well does it connect to Xn. So what is the probability of Xn given Wn? That's what Un is. And instead of talking about this probability, this log probability of Wn given Wn minus 1, I'm going to talk about the pairwise term Wn minus 1. So I've moved everything including the log. Now remember, when we did the log trick, we went from talking about potentials to talking about cost. Makes sense, right? We wanted to maximize the probability just a slide ago, which means we're maximizing the probability. Now we want to minimize the cost. So we're going to talk about minimizing this whole function, which has a unary term and a pairwise term. The unary term is always looking at the world state and the data associated with it. The pairwise term is always looking at, well, it's called pairwise for a reason. Pairwise, pairs of world states. Just Wn and Wn minus 1. Everyone's comfortable now? If I say unary cost, you know, oh yeah, I want that to be small. And I know that's the connection between a world state and its data. Yeah, unary and pairwise. Good. All right, so that equation moved up. We want to find the W states that minimize this equation. We're going to do it using dynamic programming, and we're just going to use a specific instance of dynamic programming called the Viterbi algorithm. It's very handy, and you're going to implement it this afternoon. So this was our hidden Markov model. It's just a copy of the same thing. The thing I'm going to do slightly differently, and I might need to erase a bit to represent this, is I'm going to draw this node, W1, in an expanded form. W1, I'm going to draw it sort of like this. And next to it, I'm going to draw W2, and I'm going to draw it kind of like this. And there's still going to be an X1 associated with it, but we'll just kind of draw it off to the side here. This is our X1, this is our X2, and so on. Why am I giving myself so much space? Because I'm going to do this kind of representation. These circles are circles. They are not random variables. There are no random variables inside of them. I'm just telling you that W1, this thing, has 5 discrete possible values to choose from. Okay, so this is W1 equals 1, W1 equals 2, W1 equals 3, down to W1 equals 5. So these are all the possible states. So we're just drawing a little circle here, 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 and here. Those circles are those circles. So please don't confuse them. I can completely understand why it might be confusing. Please, when you see this layout, right, think of this is all W1. This is all a random variable that can take one of 5 states. There is a random variable here, a random variable here, and another, and another, and another, and that's our last one. So we're just going to do this example here. We've introduced our unary cost and our pairwise cost. Unary cost is the relationship between, can you see this? W1 and its X1. It specifically means probability. Let's go back. The unary term is the probability of Xn given Wn. There we go. So it's the probability of X1 given W1 equals 1, or the probability of X1 given W1 equals 3, or any other version of it. For W1, let me go to here. For W1 equals 4, the unary cost says, you know what, if you saw those pixels, what's the probability that we are in state 4? The unary cost here, for k equals 2, the unary cost here says, oh, if you saw those same pixels, what's the probability that we're in state 2? Yeah? So we're just writing up here in the corner, we're writing the unary costs, and the pairwise costs, well, they're about the edges. So if I say, okay, for this W4 to be in row 3, so it's in state 3, and for this one to also be in state 3, there's some pairwise term, pairwise costs, right? Pairwise between nodes 4 and 5, between the value 3 and the value 3. So we just have a unary cost on each of these circles, and we have a pairwise cost connecting each pair of them, whether they go across or whether they go up or down. This one obviously connects to each of these. I've set it up. Is the setup clear? Sorry? Yes?
What the x's?
The x's. The probabilities, the conditional probabilities of our world state on our x. That's captured in our unary costs here. We're just writing it in, saying the unary cost of this circle represents the cost, the probability of W1 and jointly with the observation x1. This one, this whole column, all these unaries are only looking at x1. All of these u's are only looking at x2. Yeah?
We also have similar states. But
X is continuous, we said.
Visible, and so we know them.
We know them. Someone has come along and said, I'm going to evaluate this normal distribution. I'm going to evaluate your x1. How well does x1, how much does the pixel combination of pixels we're looking at look like this pose with my hand here, plus or minus some sigma for the noise? Yeah, that's captured here with this unary cost. All right. So here's the algorithm. It's fairly straightforward, but we'll walk through it. We're going to accumulate the sum cost to each node, and our goal here is to find the minimum path through all of them. When we find the minimum path, we're going to follow these steps, but when we find the minimum path, that's telling us that, that is the best explanation for what was the person's gesture here, then here, then here, then here, then here. If I only looked at one at a time, I might mistakenly think they were saying a jumble of words because one of these might have been ambiguous, right? There might be a word here that is quite ambiguous, but becomes less ambiguous when you look at the pairwise terms. Is that okay? So we're going to try to find our cheapest path that goes through all of this data. So here's the worked example with some numbers involved. So we've got some numbers here. That's a unary cost. That's a unary. And we've labeled the pairwise cost. So we're just saying, you know what, maybe someone just speaks slowly. So we'll just assume that to go from state k equals 2 to k equals 2 is 0 cost. To go from state k equals 2 to k equals 3 is a fixed cost of 2.0, right? These are some numbers someone handed to you, although you could have learned them. And this is also the state to go from state k equals 2 to state k equals 1 also happens to be 2.0. To keep from the lines overwhelming us, we're saying to go from state k equals 2 to k equals 4 or k equals 5, we'll just say that's infinitely expensive. You can't afford it, and therefore we're just throwing it out of here. In MATLAB today, you're just going to put values of like 100 here, so that it doesn't ever get chosen as a viable path. Unary costs, pairwise costs. All right. So we're going to go through at the beginning, and we're going to say, right, starting at the beginning, what is the cheapest path? What is the least expensive cost of getting here? And then we're going to ask the same question here. Well, it's a unary term, and there's nothing before it, so it's just the unary term itself. So that 2 is going to go inside of the circle. That's our accumulated cost so far. And that 0.8 went in there, and so on. Okay, so it seems like a pretty trivial step. For now, we're just going to repeat the step, but we have to be careful now. We're going to say, all right, what's the cheapest way of getting from the previous column to this circle? Well, we could have started here with a 2.0, added 0 cost. That would have gotten us here with a cost of 2. What other paths are there leading into this circle? Well, there's also this green one. We could have started with 0.8, added 2.0, so 2.8. 2.8 is more or less expensive than 2? More expensive. So we don't like that one. So we'll probably put the total cost here is 2, that's the minimum, and we'll note that we got there using that path. Not only will we note that, we'll also add in the unary cost at the end, the unary cost of that node by itself. So 2 becomes 3.1. Yeah, I can go back here, right? And you're seeing that the cheapest path was to just go straight across. Here, the cheapest path was also to go to straight across. But what you might notice, though, is that 2 different states in world node 2, in W2, prefer to start from here. Okay, we'll just note that and keep going. And we're just going to keep doing the same thing. Here we're going to say, all right, what are all the paths that lead here? Well, there's one going straight across, that's 3.1. And there's this one, that's going to be 7.6, 5.6 plus 2, right? So the horizontal one wins. We keep going and going until we get all the way to the end.
So actually, when we are going to write it at each step, we add costs of the path to the state where they go.
That's right. We add the cost. So when we're deciding who's the cheaper option, the red one or the green one, we figure out which is the cheaper. We add this unary cost. There's no escaping that unary cost. And we write that in here as the accumulated cost of getting to this node. We could pay more to get to this node if we had chosen something other than the cheapest path. But we know that we've identified the cheapest path in terms of going to the right. And so that's what we're writing in here, is the cheapest path that we've seen so far.
Right, but before we know what's the cheapest path, we have to create a list for each node with a ranking of the paths.
We can't create, what do you mean before? At the time of evaluating the cheapest, what is the cheapest path here? You can imagine saying, okay, what paths lead to me? Oh, there's 2 of them, and then yes, you sort them according to the cheapest one, then you say, oh, that's the cheapest one. Yeah? Okay. So we do this until we get to the end. When we get to the end, we see that, oh, we're running a little over time. When we get to the end, we see that we could get to world W6, and we might have incurred this cost, 19.3, 22.7, 17.4 is the cheapest one. So for W6, that's the winner. For W5, who do you think is the winner? Speak up. 13.3. So K equals 5. Because we just traced backwards. There's only one way you can get that cheap cost. If you went from any of these, that wouldn't be the cheapest. So to get here, you had to go. Now you just trace backwards. You had to go from here, and to get here, you had to come from this circle, and back, and back, and back. And those are the best states, best values of K at each of the successive nodes W1 through W6. Okay, so, right, so I guess we just did that. Trace it back, that's what you get. A quick note here. Based on seeing dynamic programming, a predecessor for you guys did a master's, did this, saw this lecture, and then when he graduated, he was doing some consulting gig where they were trying to find the best combination of states. And they said, oh, well, it's this exponential problem, right? We wish we could solve it faster, but we just have this supercomputer set up to try to evaluate all the possible combinations, right? And possible combinations are what? If we have 3, 4, 5, right? So it's 5 to the 6th power, right? Which is like 25, 125. It's 15,000 something. Yes, I got the 3,000. Okay, 15,000 something. Versus if you just do dynamic programming, you should only need 150. So the complexity of this is much lower, and this graduate made something like 40,000 pounds on that implement, just using the code basically from your lab this afternoon. Okay. Final thing I'm going to show is exactly the thing you're implementing today. So I know we're running a little late, but I hope it'll be worth it. You're going to work on stereo. World state in stereo is going to be disparity. Now, what does that mean? I've got a left image, I've got a right image. If I look at the xy coordinates of that point, right, and I know that that's the same point as that, the xy coordinates of this in my left camera, are they the same as my xy coordinates of that same object in my right camera?
No.
No. They're going to be shifted a little bit. They're going to be shifted based on what? The depth, the distance, right? Which way? If the distance is big, are they going to shift? Is that going to shift more or less? So further away, it shifts less. Closer, it shifts more.
Actually, it depends on the point of focus of the camera. The standard reverses and it shifts more.
You cannot get. I don't think you can reverse this relationship. Yeah, you can blur the point spread function, but you cannot reverse this relationship. Bigger distance just means smaller disparity.
Right, because when you go away, then it also becomes smaller, so probably it just offsets.
So let's say it will adjust the point spread function, and so you will potentially have a different behavior if you have camera 1 in one focal depth and camera 2 at a different focal depth, but you will still, for that same pairing of cameras, closer objects will move more pixels. The amount of pixels, the distance in pixels, because we can think of pixel sort of the space between pixels, that distance is what we're referring to as disparity. How disparate, how far away is that from its corresponding location in the new image. All right, so that's our disparity. We're going to model the world state, right, as our disparities. So world state is going to be a set of discrete possible disparities. Yes, I know things could be sort of at various continuous distances. We're just going to quantize that, and we're going to say, all right, there are 10 possible disparities, and your object is at one of them. So W is going to be discrete, and our observations X are just going to be our intensities. The thing I want to show you before you go to the lab, you're going to be implementing this, is that, yeah, that's the ground truth. That's what you wish you could compute as a stereo. If we look at an individual pixel, like I guess that's from here. No, that's from here. Very good. We might say individually, if I go for that pixel in image 1, I'm going to go for a search on the scan line in image 2. So stereo is all about searching. It says, I know that you are somewhere on this scan line in image 2 because I've calibrated the cameras and done some rectification. We'll talk about that in coming weeks. You're somewhere on the scan line. Where are you? I'm going to check at a bunch of different disparities, and I'm going to see where you are. The disparity graph might look like this for the red pixel. It will say, oh, for a low disparity, right, it's very, very bad match. Here we've got white compared to some blue, right, so that's very bad. As I sweep across, you can kind of look at this zoomed in version. As I sweep across, I might see that, oh, look, when I get to the right place, the right W, there's a very good match. The RGB values, they really correspond between that and that, or i.e. between that and that. If I look at any other combination, that versus that, you're back down to these low values, this bad match between the RGBs. Okay, so we're hopeful that there's this peak. In some parts of the image, like this area where there's not much texture around this green pixel with the green square, right? So it's a dark pixel. We'll do the same thing. We'll search in the image too for a bunch of different possible disparities, and there we'll see that it is constantly high. So that matches that just as well as it matches that, matches that, matches that, matches that, matches that. Basically, we're not seeing any peak here. This is the RGB values being plotted for one match and for the other match. In other words, we are trying to localize what is the right disparity for the pixel with the green square, and we're failing. We're not sure. Normally, if you were solving for the world states of every pixel in image 1 independently, that would be good for the red pixel, bad for the green one. We're using dynamic programming because we want to say, look, if there are some places where you know the right answer, where it's quite obvious because there's this peak, then that can help you get past the periods where it's quite ambiguous. So this picture shows you the disparities. This is just a color encoding of disparities based on every pixel for itself, completely independently of its neighbors, no Markov, hidden Markov model assumption. If you do scan lines, if you connect each scan line of pixels into a chain, as you will do in today's lab, you'll see that, well, you should just see this as being better than that, right? These areas of low texture, they're pretty good. They're not randomly choosing to be some other disparity. They're actually staying pretty consistent. You could complain and say one artifact is here that they are creating these streaks. Now remember, just because we're implementing this from left to right doesn't mean the streaks have to go left to right, right? Because of our dynamic programming, we're finding the optimal path through all of the nodes, and that means that we prefer to stay at the same disparity during a scan line, because there's like this very minimal cost or zero cost of keeping a pixel and its neighbor at the same disparity. But there's a non-trivial cost to change disparities. And so we get these kinds of streaks. That's what you will be working towards today. Next week's lecture, we'll be dealing with grids, so not just chains. So we get rid of those streaks. But right now, don't worry about that. So if we have 28 people, we will fit in the lab. If we have more than 28, we might need to kind of work on laptops and bide our time until 4 o'clock when the other lab becomes available. Where are the extras from the chapter 11?